So when I described current density previously, I failed to mention on purpose a minor detail, right? It's minor, but it's important. When charges are subjected to a potential difference in a wire and thus an electric field, they don't simply move unhindered, right? They don't move freely unperturbed. There is some natural resistance. If you think about it, this should make sense. What are these charges moving in? What's the medium? Well, these are free electrons. They're the valence electrons, essentially. And so they're moving in between the crystalline structure of the atoms that make up the wire itself. Whether the wire is made of copper, silicon, glass, plastic, whatever, right? Charges move physically in between these atoms. So there is some natural or intrinsic resistance to their flow. So if you remember, the current can be written as, well, charge per time, or it can also be written as the number density times Q times the area, and then V, right? The average speed that a charge moves along a wire. This is also known as the drift velocity, so you can write that as V or with a subscript D, right? In a wire, there's also a charge density, J, which is, well, the current divided by the cross-sectional area, and thus that's in Q times that drift speed, V. Okay? Now, if a wire is connected to a battery, there exists an electric field in that wire. Yes, this is where the current comes from, right? So we can say that the current density J, or in other words, the current, is directly related to the magnitude of that electric field. Whoops, I gave it away. It's related to the electric field by some constant, right? The constant of proportionality, in other words. And this constant is known as the conductivity. The conductivity of that wire material, right? And that's the Greek letter sigma. And by convention, that means, well, the ability for a material to allow charges to flow within it. Right? That's what conductivity is. Some materials like copper or a metal in general have a very high conductivity. They allow charges to move through them very easily. Other materials like glass, wood, or rubber have very low conductivities. And so because of that, they're known as insulators. They inhibit the flow of charge more than they allow it. And so this is what's known as Ohm's law, or rather Ohm's law version 1. Ohm's law version 1. Let me show you not a better way, but a different, more common method to write Ohm's law. Let's rewrite J as the current over area, unvectored for right now, and sigma is there. The electric field in the wire, well, going back 2 chapters, I think, potential is integral E dot, I'm going to use L because that's what my picture is in terms of. This simply is E times L, right? So the electric field can be written as the potential divided by some length, right? The length of wire, presumably. And then rewriting that equation, we have I times L over A times sigma equals the potential V. And now, circled here, each of these properties, or each of these values, I'll say, for a given wire will not change. For a given wire. They are properties of the physical nature of the wire itself. Right? The length of that wire, the cross-sectional area or thickness of that wire, and the conductivity of that wire. Those are all physical properties. And so we give that a variable name known as the resistance. Resistance R. And now this is the more common form of Ohm's law. Call it version 2. Okay? V equals IR. The voltage supplied from a battery or some source is directly proportional to the current that flows in a wire connected to that source. It's related or proportional by the amount of the resistance, and that's a constant for a given wire. Again, you can change out wires, you can cut wire in two, right? But if you connect a certain length of wire, a certain thickness of wire, and a certain material to a battery, the flow of charge will be directly proportional to the voltage supplied. Right? The resistance is completely independent of either of those, and that's the important thing here. The resistance R is independent of the voltage or current. Okay, it's its own value, right? The resistance comes from the physical properties of the wire itself. Okay, and because of that, when we graph, or if you were to graph the potential versus current, it would be a straight line, right? With a slope of R, if you will. M equals R, if you will, right? And let's take a look at that resistance just a little bit more. L over A times sigma. You can write it like that, or you might see it written like this. Rho times L over A, right? Rho, in this case, is the resistivity. Resistivity. Rho. Rho and sigma are inversely proportional, which should make sense if you think about it. A material that has a very high value for conductivity, right? 1 over a large number is a very small number. So a material like copper, high conductivity, low resistivity. On the flip side, materials like wood and rubber have very low conductivities, so 1 over a small value equals a very large value. Okay, so if we were to graph it, this means for a given potential, you have a low current, a small current. And so this is for, what is this, a high resistivity. Materials with a very low resistivity or high conductivity are graphed over here. Okay, still a linear relationship between the two, though. Okay, so I hope this has given you a little bit of insight into the relationship between voltage and current and resistance and resistivity. Here's a table of a couple values, right? And see the resistivity for a typical wire is composed of copper. It's a very low resistivity, very high conductivity, right? So it's relatively cheap, and that's why it's used almost universally in electric circuits, right? However, materials like rubber or glass or silicon, high resistivities, low conductivities, that's why they're typically used in dielectrics, right? Or as an insulator, right? So, yeah, there you go. Thanks for watching.